Louisiana Flood Attribution Study. The Louisiana flood is the most extreme and expensive event since Hurricane Sandy. And what's unique? Well, we didn't quite see it coming. This is evidenced by the FEMA estimate of housing property loss. It even surpasses Hurricane Katrina. What we wanted to do is to get past probabilistic assessment and attribution because the probability of an extreme event like this keeps changing. We wanted to know the mechanism. From media meteorologists and weather reports, the prolonged and intense rainfall has been attributed to an unnamed cyclone. Some called it a land hurricane. This low-pressure system dumped 3 times as much rain in the state as Hurricane Katrina did in 2005. But climate projection studies found inconsistent trends in Atlantic tropical cyclones, with uncertain future for hurricanes in the Gulf of Mexico. What we found in the synoptic process is more complicated, involving a mid-latitude system, a fast-moving short-wave trough. You can see that this short-wave trough briefly interacted with the low-pressure system. The northerly wind met southerly flow, and this creates moisture pooling. The jet stream exit formed strong upper-level divergence. We also computed the vorticity budget at upper and lower levels to examine their interaction, like how they collided and induced vortex stretching. Such an interaction of the two, inherently independent weather systems posed a challenge to forecasting. Neither GFS or CFS could predict the elevated precipitation in Louisiana 2 days before it occurred. The seasonal prediction, like these 1-month NMME precipitation forecasts, also did not capture any probability of higher than normal rainfall. This may be also contributed to the lack of connection between Louisiana and prominent climate modes, like the El Nino. Under this circumstance, we felt that an investigation of this particular type of extreme precipitation event is necessary. Based on the synoptic conditions on the left, one can apply spatial filtering to depict the lower level cyclone with wave number 9 and above, under the upper level anticyclone with the longer wave numbers, which show an incoming trough to the west. It is important to capture the stand-alone low-pressure system embedded in an upper-level ridge, which suggests minimal synoptic forcing. Next, the criteria were applied to the 11th of August through 14th to depict the evolution of the two systems. I then used the pattern correlation to detect similar events. These criteria have to be met at both levels. Bar 1s, and here is the composite based on the low bar criterion. We can see the isolated low-pressure system at the location similar to the August 2016 case, underneath the predominant anticyclonic upper-level flows. There is also increased precipitation in and around Louisiana. The occurrence of those similar cases are presented as the box and whisker plot, summarizing the case selections within those low bar and high bar criteria. Each box plot contains 49 combinations of the spatial correlations, and with the tracking completed, we can see how or whether similar weather patterns have happened in the past. Here shows 2 periods, the post-1979 era and the post-1948 era. The next plots show the composite precipitation over Louisiana averaged from these identified cases. The amount wasn't as large as in 2016, but these results show that similar events did exist in the past and are not unprecedented. Notice here that there is a tendency for more in concentrated cases after 1990, which prompts for the next analysis using projection simulations. This is the result of the same case tracking applied to the CISM Large-ensemble project data, with 37 members each. There is a noticeable increase in the even precipitation over Louisiana. There is also an increase in the case number. The increase in event precipitation can be easily attributed to physical processes, such as the projected increase in the precipitable water in the Gulf Coast area. One of the extreme measures of the 2016 event was the record amount of precipitable water immediate before the flood, but the increase in the case number is a bit more puzzling. What we found is an increase in both the upper-level trough and the low-pressure system, with a steeper climb in the upper-level trough. Why? It might be related to the documented amplification in the quasi-stationary short waves, especially during summer. Here, the August 2016 circulation anomaly shows a distinct short-wave pattern, with a cyclonic anomaly over the western US. By comparing with the post-1985 trend in the circulation, a very similar short-wave pattern stands out, suggesting that the August 2016 situation may be part of this long-term trend. Interesting, the CISM also projects a similar short-wave trend as the pattern of future change, although the cyclonic anomaly is slightly shifted to the east, over the Great Plains. To quickly summarize, these results mean that the chance for mid-latitude short waves to interact with southern low-pressure systems has increased and will increase. The details of these analyses can be found in our paper, which was just published in the Geophysical Research Letters. So let's move on to why this analysis matters. I think the first and utmost challenge lying ahead is the current inability to forecast such an event as in Louisiana. The randomness and complex interaction between these two independent weather systems are just too difficult to forecast. I'd like to make a comparison with another recent extreme event here, the 2015 Texas flood. The Texas flood showed a traceable large-scale modulation, and it coincided with the rainy season, which is the late spring when, climatologically, the passing synoptic troughs tend to interact with the Great Plains low-level jet. Seasonal forecast was able to capture the rainfall anomaly at a long lead time. Let's take a deeper look. The El Nino teleconnection played an important role and it has amplified. Here shows the intensified tropical wave trend since the 1980s. The amplified teleconnection helped enhance the spring trough, which then produced more storms towards Texas. But more importantly, The subseasonal prediction did a good job in capturing the Texas wet anomaly, even with a 3-month lead time. Here I'm showing the NMME forecast. This good skill is largely due to the relatively better model capability in depicting ENSO and its teleconnection, as well as the seasonal cycle. Again, I skipped a lot of details here, and will refer these to our GRL paper of the Texas flood. The second issue here comes to challenge how attribution is made. Many of you may know an attribution paper was published almost within 1 month of the Louisiana flood. This is a long and comprehensive paper, which also signifies the modelling community's capability in near real-time and perhaps automated attribution, mainly for probabilistic assessment, like the return time. But we still face this challenge of comparing apples to orange, because a similar event or Louisiana-like event is not the same event. Besides, return periods keep changing. So we picked a dynamic downscaling approach with large ensembles to attempt a quantitative attribution by removing or doubling the warming trend after 1985. We found that the post-1985 climate warming may contribute to about 20% of the precipitation intensity. We are not sure how useful this information is, but at least it was fun to do. The third and last challenge here concerns how we deal with weak systems. Impending hurricanes would trigger a long list of warning and disaster prevention procedures. Unnamed or weak cyclones don't. Cyclones or storms without a name also make it much harder to track on the media and by society. In the case of Louisiana, it involved two seemingly ordinary weather systems with an unexpected consequence. Looking forward, I am fortunate to participate in the Hyperion project, led by Paul Ulrich. For instance, Paul has designed some automated tracking algorithm, and I am hoping to work with his team to track so-called weak systems that potentially have a high impact. And I just want to quickly remind you that similar systems have created as many damages as the famous ones. For example, here is the weak mid-tropospheric disturbance that caused the West Virginia flood. It's a weak trough that may originate from the Rocky Mountains and the ride on zonal or northwesterly flows, which won't be picked up by any cyclone tracking method. Here, I'm showing you my manual tracking of similar events, and when they interact with the low-level jet, the embedded storms can become robust. But manual tracking is time-consuming, and I don't want to do it again. Thank you.